All right, so 35. We're starting 14.2 now. And this is on rational and irrational roots. If you watch the previous video, this is like 6 seconds after it. Rational and irrational roots of polynomials. So remember, we're looking at, we have f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus, and we keep going down, a sub 1 x plus a sub 0. Now for this next thing to work, we want all the a sub I terms to be integers. They do not have to be positive. They can be negative, they can be 0. And we're looking specifically at finding roots. So we're finding roots, so this is equal 0. So if they're not integers, if like there's fractions here, multiply through until by whatever you need to clear fractions. It doesn't change the right side if I multiply through by 2 or 108. Anything times 0 is still 0. So if the coefficients are integers, all possible rational roots come in the form of P over Q, where P is a factor of a sub 0 and Q is a factor of a sub n.
Let me just take the first two.
Yeah, so I'm going to bring up that last one we did just to show you how this works and how we found a -2, 1, and 3/2 are on the list. So we had 2x to the 5th minus 5x to the 4th plus 7x cubed plus 14x squared minus 15 or 54x plus 36 equals 0. And we said x equals -2, 1, and 3/2 are roots. So my P terms come from the 36. So things that multiply to make 36 are 36 times 1, 18 times 2, 12 times 3, 9 times 4, 6 times 6. So I'm gonna say P has plus or minus 1, plus or minus 2, because it can be the negative version as well. Plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12, plus or minus 18, and plus or minus 36. There's a long list of things that it could possibly be. All of these numbers are factors of 36. Right? The Q term comes from the 2, factors of 2. Well, there's only 2 numbers that multiply make 2. Plus or minus 1, plus or minus 2. So if I do P over Q, this has got a long list with all the negatives and shit. But notice I can put 3 over 2 shows up from these 2. Negative 2 shows up from these 2. And positive 1 shows up from these 2. We're going to take one number and put it over the other. This one's got a lot. We're going to work with a smaller one on the next thing, like just to show it worked out, like how you would work it out on a smaller one. Yeah.
You're saying, because you give the series and then you put it like P over, right? P over.
Yeah, you're making a fraction out of it.
So you do like, so 1 and 1, 2 and 2, and then 1 ahead on P.
Let's show you the next step. I was just showing you the 3 combinations that work here. There's a lot of combinations on this one, like more than I want to write down because it's going to take up like a third of a page if I write them all out. There's a lot of fractions here. Only 3 of them worked. Because I could have done 36 over 2. I could have done 12 over 2.
Yeah, it could have been all.
Could have done any of those, you know. The negative versions of them. Let's start off with a simpler one. 6x to the 4th minus 3x cubed plus 2x squared plus x minus 4 equals 0. My p's come from factors of 4. So what things can multiply to make 4?
1, 2, 4.
1, 2, and 4. So plus or minus 1, plus or minus 2, plus or minus 4. Q comes the first one, 6.
1, 2, and 3. That's 6.
And 6, right? So let's make a list. First, we're going to put 1 over each of these. So I could have plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 1 over 3, plus or minus 1 over 6. I'm going to do this for all of them, and then we're going to cancel out things that repeat. Then we're going to do the 2 over it, plus or minus 2 over 1, plus or minus 2 over 2, plus or minus 2 over 3, plus or minus 2 over 6. So these are my P over Q combinations. And finally, the 4, plus or minus 4 over 1, plus or minus 4 over 2, plus or minus 4 over 3, plus or minus 4 over 6.
Six.
What?
6, 2.
No, the P is the only thing that goes on top. This is a pretty big list. But we have some repeats, right? 2/2 is the same thing as 1. And this is a 1 as well. So these two are the same. 2/6, maybe I'll do a different color here. 2/6 is 1/3. And I have a 1/3 here. Four over two is 2. And I have a 2 right here. And 4/6 reduces to 2/3, and I have that there. So if I trim my list down. This one's here, I'm gonna cross it out to make it easier to track. This 2 is here, I'll cross that out. 1/3 is here, I'll cross that out. And 2/3 is here, I'll cross that one out. So I got 1, 1/2, 1/3, 1/6, plus or minus 2, plus or minus 2/3, plus or minus 4, plus or minus 4/3, and that's it. Smaller list than we had a second ago. And then I'm gonna sort these. I'm gonna put them in increasing order. So the smallest number I have here is 1/6. Then I have 1/3. Then I have 1/2. 2/3 is larger than 1/2. Then I got the 1. Let's see, I'm gonna put little check marks over them after I've done them. Then I got 4/3 is bigger than 1, but less than 2. And I got plus or minus 2, plus or minus 4. Now, you're probably not gonna like it, but bear with me on this. I'm gonna write these out from the lowest number to the highest number. So I'm gonna start with this end and I'm gonna write -4. I'm just writing them all without the plus or minus in numerical order. And there's a reason for this. I'm gonna go down the list with the negatives. And then I'm gonna go back up the list with positives. Those are all our combinations. Okay, so we need to find two numbers before we can get this down to an x squared, right? We can just guess and check all these numbers, plugging them in until we find a 0. Okay, we talked about earlier the remainder theorem. If we plug it in and we get a 0, then that's a root. We can plug and shove this on a calculator. There are, like, we can go left to right if we wanted to. There are some theorems that'll help narrow it down. So let's put that. We could plug and chug. F of P over Q. And look for f of p over q equals 0. Until we find 2. Use synthetic division and get down to a quadratic. Or we could keep going, but I think once you get down to a quadratic. It's faster because the last ones may not be rational. To get down to a quadratic. And solve. Tripod in my head now. What a great song. So there are some things that help us. We have something called the upper and lower bound theorem. If b is greater than 0, so like a positive number, and we try, so we're trying x minus b basically. We try x minus b in the synthetic division. And the bottom row is all non-negative. So positive or 0. Then there are no roots larger than b. So that it's like this is like an upper boundary. I don't know if we have any on this list, but yeah, we do. I know of at least one on this list. So let me show that one real quick. I'm pretty sure if x equals 1, if we try x equals 1. All of these are positive. So there is no root larger than 1. And x equals 1 isn't either. Because we don't have a remainder of 0. So that doesn't cross off a whole lot, but it does cross off the 4/3, the 2, and the 4, right? So what this says is that theorem crosses off The 1 doesn't work, the 4/3 is out, the 2 is out, the 4 is out. Now, there might be a lower number that works, but I saw immediately that 1 worked. Anything to make the list smaller.
Anything above one value is out. Because of that.
Yeah,
Not because it had a remainder. but
it's because the bottom row is all positive. I wonder if he has Descartes in here.
What if the original problem, it just happens to be all positive?
Then you can literally knock out all positive roots.
Oh, okay.
That's a good question. If, so this is fun. If they are all positive to start with. There are no positive roots. Because there's no way to get the number to go back down to 0. There's no way to introduce a negative. All right, so that's the upper bound version. The lower bound version is similar, but a little different. So the lower bound part of that, I'll use a lower b, case b here. So we're gonna say b is less than 0, and we're looking at x minus b. If the bottom row alternates signs. With 0 counting for either to make this happen. Then there are no roots less than b. This one's a little harder to find without just getting lucky. He has it in here. Make sure I got the right name because it's helpful. Eyeballing this, I don't know if there is a negative one that works here. But there might be. Something else you can do here is called the Descartes rule of sign. Descartes rule of signs. The S, this S is silent, the cart is. That S, not that
Yeah.
S.
Yeah, it's gonna be.
It might be.
Oh, yeah, Renee Department,
Is it the same guy?
Is it?
That's the name that I thought.
Then, there's a philosopher named Descartes.
yeah, no, it's the same
spell,
yeah.
it's 100% the same.
DESC.
So we're talking about someone's thing, we have a plural, we. Like if it's Davis, it's Davis's sign, if it's David, it's David's sign, so there's an S on it either way.
In English.
Well, I'm fucking teaching in English,
Fair enough.
so you're gonna have to get over that.
Fair enough.
At least that S is silent. And in English, we have an S on the end for possession. All right, so whether the apostrophe is in the right spot or not, I don't fucking know. But it's pronounced that way. All right, so how does it work? Count the sign changes. This is the maximum number of positive roots. So how many times does this function change signs? Positive to negative is once, negative to positive is twice. There's no sign change here. But there's a third sign change here. So on 6x to the fourth minus 3x cubed plus 2x squared plus x minus 4 equals 0, there are 3 sign changes. Which means 3 positive roots. Max.
A sign change being from positive to negative.
Positive, negative. Yeah, so the coefficients change signs. Then plug in negative x. If you plug in negative x, now count sign changes. And that's the number of negative roots. So only 1, right? That's a little more work than I want to do though.
Yeah.
Right? You can eyeball it in your head. The even ones change signs or from whatever they were. Or don't change signs, the odd ones change signs, but I don't even need to do all that. What did that polynomial degree rule tell us? The degree is 4, because the exponent's 4, so there's a max of 4 roots. And if 3 are positive, max of 1 negative. Those should add up to the 4 or the degree every time. I've yet to see it not add up to the degree. I've never seen it worded that way, so I'm wondering if there's a questionable section, but it's usually a good rule of thumb. So how does this help you?
That tells us it's exactly.
If there is a negative root,
If
and if there's a good chance there's a negative root, but it may not be rational, it may be irrational. But look at our list. Even before I crossed shit out, I had an even number of positive and an even number of negative roots. If I have 3 chances to get the right number in a positive side, and only 1 chance to get the correct answer on the negative side, which number should I be trying?
Negative.
The positive. I got 3 chances to hit the right number.
3 out of 4, yeah.
Yeah, I've only got 1 chance of getting the correct one over here. Focus on the one that's got more options here. So we'll focus on positive roots. There's one other theorem here. We'll finish this problem on Tuesday. But there's one other theorem here. If you start working on it and want to think about it. If you try 2 different ones. Let's say A and B. Because the numbers are going to change for each problem. If f of A and f of B have opposite signs. Or the remainders are opposite signs. If you're doing synthetic division. Then there is a root between them. Must be a root between them. But it may not be rational. And I'll give you we'll do this graphically to see what's going on. I'll do 2 different options. I did f of A. What is that value really on a graph? The y value of the point. So this is saying if f of A is greater than 0 and f of B is less than 0. I don't know where they cross. But it's got to cross somewhere. Right? You're assuming a continuous line. Polynomials are continuous. So it's got to cross somewhere.
So you should try all the values in between those.
Yeah, try all the values in between. And if none of them are it, you know there's an irrational root in there, and you got 1 less root to look for. The other option would be f of A is less than 0 and f of B is greater than 0. It's still got to cross somewhere. But if they're the same sign, it may or may not cross. So how do you use this tactically in it? Putting all these together. Check Descartes' rule. And try numbers that have more possible. Try the values with more possible roots. So in this case, we try positive numbers. Don't try consecutive numbers. at least have a gap in there. Like, I know 1 is out. If I tried 1/2, I would try 1/6 next.
If we go to Desmos, will it give us a graph of the equation?
I'm sure it will, of course it will.
Oh, okay.
You don't get that on the test though. So that's only useful for verifying your answer.
Yeah,
Okay, so like I would alternate here, because if I try 1/2 and 1/6. And there's a sign change. Then I know 1/3 is a good shot. But if I just keep trying them in order, I can't take advantage of that last theorem. So avoid consecutive thing, because that way you can like see if they change signs. Also, because of the whole upper lower bound thing. Start closer to the end. But not at the end. To try to use the upper lower bounds. Oh shit, it's fucking 5 o'clock.
oh,
Just to finish off the, like, mentally the idea here. We have a lot of P's over Q's. But by checking the Descartes rule, it says focus, we saw the focus on the positive. By doing the upper bound rule, I recognized, like I eyeballed it in my head, and I thought, I think one will be all positive in the bottom. But I didn't try the end, and I didn't try either end. Trying this out, eliminated all those. I've only got 4 positive numbers left. And 3 of them could be our roots. Now, there might be positive square root of 2 or something in there that's not going to show up.
Moreover, there are 3 out of 4 roots are positive, that we'll find out what the fourth root is if.
Right. Yeah, we only need to find 2 of them, because down at that point, we're down to a quadratic. Quadratic's faster.
So we can plug in 3 as a 3, if we plug in 3 with 2, we have really high chances of finding
Right.
all ones.
So let's see how many numbers are here. 1, 2, 3, 4, 5, 6, 7, 8. There were 16 numbers here. By taking advantage of counting the signs, I narrowed it down to just trying the positives first, because there's a better chance of hitting. Hitting the 1, I've done 1 attempt. I've narrowed it down to 4 numbers left. So I've got a maximum of 5 different numbers to check here rather than 16. Before I start, I can narrow, like, rather than having to check all 16, I narrowed it down to 5, and probably if I get 1 of them, I can narrow it down even more, doing just like doing gaps, and if there's something different. There's a way to narrow it down. We will finish this problem on Tuesday. We'll do some more like this on Tuesday. There's a lot of rules there that we covered. Godspeed. Final is in 3 weeks. If you look at the syllabus, and we'll do that real quick. As of next Thursday, we will have finished chapter 14. The week after that is chapter 15. Chapter 15 will not be on your final. You will see the topics again in like calculus and stuff. So I need to teach them to you, but you don't have a whole lot of time to do the homework on them. So I'm not going to test you on them, but they might be extra credit on like the test. It is still part of the homework. And next week I will open up all the homework. So like anything you've done in the past, if you did it late, you'll get credit for having what you did late. Have a good weekend.
so you go, your next class, but not 54. You're not gonna use allocated, are you?
No,
Okay.
I'll probably use my math lab.
Yes. I'm just gonna send out the